without further ado, we'll move on to our next speaker, which is Ben Albrecht from Hewlett-Packard Enterprise, talking about HPC workflow management.
Thank you, Lydia. Okay, so I'm going to talk about HPC workflow management with CHIUW. So just for some motivation, users in the HPC community have for a long time suffered from this challenge of coordinating running many monolithic applications and dealing with, both launching them on these HPC systems with varying workload managers and launchers, as well as dealing with the outputs that they produce. And this impacts scientists and engineers across many domains, including astronomy, computational chemistry, in my own experience, bioinformatics, data science, and so on. So the typical process that a user might go through is they will start with a simple shell script or maybe a collection of shell scripts to run these codes, to launch their applications and maybe do something with the output or do some preparation with the inputs. And over time, as I'm sure many of you have experienced in your own work, this can really become unwieldy as the complexity of the project or complexity of the workflow grows with the maturity of the project. And so at some point, users, if they are unable to continue with the shell scripting path, they must make a decision if they want to move towards using something like a workflow framework, something like Apache Airflow as like a general purpose one, or maybe a domain specific one like BioClips for bioinformatics, or they can migrate their workflow code base over to something a little more maintainable using like a more advanced programming language. And so that's the premise for this talk. Is I'm going to explore using CHIUW as a language to write HPC workflows. Earlier in the day, we've talked about CHIUW being more than just a language specifically for writing high performance computing applications. It really strives to be a general purpose programming language. And I think this is an example, even though it's applied in the HPC domain, I think this is an example of CHIUW being useful as a general purpose programming language. So to start off with some background, this talk is actually motivated by some work that we've done here at HPE on a project called Cray HPO, which is a hyperparameter optimizer. I'll talk about what that means in a little bit. I just want to point out that the building blocks and patterns that we explore in this talk are not by any means a comprehensive list of all the workflow patterns that you would see when you're writing these programs. It's simply just the types of patterns that we've encountered and how we implemented those in CHIUW, and we try to learn something from that. So Cray HPO, it's a hyperparameter optimization framework. And to kind of set that up, what that means, first, you need to, if you weren't familiar with the data science field, which probably many of you are, but maybe not everyone, in general, a model is something that's trained on a data set to make predictions about data sets it hasn't seen before. And parameters are internal values in that model that are tuned as it's training and used to make the predictions. So like the simplest model you can think of is like a, just fitting a line. So y equals mx plus b, your slope and offset are your parameters there. And then the hyperparameters would be the external values that impact how the model is trained. So it impacts the capacity of the model to learn. An example is like learning rate is a popular hyperparameter that is tuned in stochastic gradient descent of neural networks, or something like the number of trees you use in a random forest. So hyperparameter optimization, as the name implies, is the process of tuning these hyperparameters to minimize some kind of metric. Typical metric you might minimize something like 1 minus accuracy or the loss. And so there's a wide breadth of HPO strategies out there in the wild. The main 4 categories really are kind of like grid, random. These are embarrassingly parallel strategies, and then you have more sophisticated algorithms like the genetic and Bayesian, which learn from previous iterations and utilize that feedback loop to guide the optimization. And then there are many advanced variations on top of these kind of foundations, these foundational strategies that kind of make up the state-of-the-art algorithms out there today. And yeah, this figure I'm just showing you that hyperparameter optimization it's just kind of one piece of the full data science pipeline. Once you have a model established and a data set established and your features, you might try to train those hyperparameters on your model. Okay, and just so you have an example in mind as we work through this, I want to show some code of what that Cray HPO workflow manager looks like. So Cray HPO is essentially acting as a distributed workflow manager for tuning the hyperparameters. It's there's some more complex pieces in the actual optimizer, but you can view it that way. And so here's the interface. It's actually exposed as a Python interface, even though the library is written in Chapel. This is chosen because Python's kind of the language of choice for data science and machine learning, and that's its target audience. So you see we import the HPO module. We set up an evaluator, so the user specifies their training, the program that trains their model. They can set up some information like the type of workload manager, the number of nodes. Then the user defines their hyperparameter search space. I don't know if you can see my mouse here. And then they set up the optimizer with there's actually some parameters to the optimizer as well that tells it how to optimize those hyperparameters. So this is just to give you kind of the background of where how these ideas developed, and to give you a concrete example to think about as we're working through some of these workflow patterns. So now I'm going to transition over to talking about some of these workflow building blocks and design patterns that you might encounter when you're writing a workflow program. So to start at the very basics, if you're going to write an application that's gluing together other programs, at first it needs to be able to run other programs. And so in order to do that, we use our spawn module, which provides these kind of these workhorse functions, spawn and spawn shell, that allow you to just launch another program as a subprocess. So run simulation here is our little dummy example we're using. And so this is kind of the simplest spawn example you can come up with. We're just spawning a process and we have the handle to that, and we're not doing anything with it. A little more advanced example, just want to point out that so spawning a subprocess is a non-blocking operation by default. So if you wanted to block on the waiting for the output to complete, or waiting for that program to complete, you would call wait or communicate method on your process object. So this is a little example of that. We create a subprocess for run simulation. Now we're piping out our standard out. We're going to wait on that subprocess to finish, and then we're going to loop over our standard outs and print out the lines. So pretty simple building blocks here. Okay, next up, say you want to launch on a distributed system, and your subprocess needs to be distributed. So one way you could do that is take the previous example I just showed and just put in the necessary command line arguments to launch with the specific workload manager that you're using. Say like Slurm, you do like an salloc and then an srun with your program. But what you might do, you might build up a nice interface to these workload managers as we did in Cray HPO. So here we have an example showing our Slurm module that we built, has a nice interface to Slurm. So you can do an SLOC, pass in a number of nodes, timeout in units of minutes. You get a job ID from that. And then you can pass that job ID into further functions of the interface, such as srun, and then that will run 32 node instance of run simulation on that allocation. And then you get back the same process, same subprocess that you would for any spawn call. So we can query information on that or just wait on it as we're doing here. And to take that abstraction one step further, we can go ahead and abstract away all of the workload manager specifics to enable a portable API for any HPC system that I guess that you're accounting for in your implementation. So what we've done here is we've created a jobs module, and this jobs module is providing a common API to do all of the typical operations you would do on an HPC workload manager. So here we're creating a new job. We're specifying the workload manager is going to be, we're using a PBS workload manager and an app run launcher, and we are going to allocate 32 nodes for 2 hours and just run that, run the simulation code with 32 nodes in a distributed fashion. And we get back a processor type. Okay, launching subprocesses in parallel. So, so the Forall loop is really the ideal construct for the functionality of launching multiple subprocesses in parallel, which is necessary for many workloads. So what's nice about the Forall loop is it, as we all know, it creates a concurrent task, set of tasks that are mapped to the available resources, such as your cores, GPUs, or nodes. So taking a look at this example, we have these simulation commands array of strings. So these are going to be the commands that we need to run, like run simulation with some arguments. Just pretend we have a way to get those commands. And then we're going to do a for all over those commands, and then go ahead and spawn those simulation commands in each task here. So in this example, this would be ideal if what you wanted was to run a single instance of the simulation per task, per core available on your local machine, assuming this is running on a local machine and with chapel_com equals none. But we typically, for an HPC workload, we're going to be we want to map these resources instead of cores to on our machine to say a number of nodes. So this is how we would do that. We would take in a number of nodes per simulation that we want to run, a total number of nodes, and then down here we can actually just divide those and get our number of parallel tasks that we want. And in our for all loop, we now explicitly call the default rectangular array parallel iterator using this. This isn't really the long-term interface we'd like for this, but this is kind of the way to get at the real default rectangular array underneath, and to call that parallel iterator. So you're calling the underscore value dot these, and you can override the task per locale here. We're sending it to num parallel tasks. So now we're running a for all loop over this number of simulation commands we want to run, with the number of parallel tasks equal to the number of nodes available. So that for all is basically managing our entire workflow for us, where it's just chunking up your work and running the number in parallel that we'd want at a time.
Hey Ben,
Yes.
This is your time check.
Okay. Oh, okay, right. Thank you. All right. So getting close to the end here. So this last example I just want to show is the variable number of nodes per distributed application. So this is in the Cray HPO instance, we wanted to have we wanted to have a nodes as a hyperparameter that you can actually tune, because that may actually impact your time to accuracy due to a number of reasons. So this is just a quick example showing how you might implement that. Here we're actually using the chapel locks. It's an internal module. It's not publicly documented yet, but that is, it's basically just a clean interface to, kind of wrapped up interface to atomics, where it's optimized for cases where you don't expect a lot of contention on the lock. So you could implement this in with just basic atomics, but I just wanted to have a cleaner interface to show here. So we're using the chapel locks, and what we do is we do our Forall over the simulation commands. As we did before, we're grabbing a local number of nodes, a random stream that we've defined somewhere, getting a random number between 1 and 8, and then we're going to wait for those nodes to be available before we allocate, or before we run on them. And so if we look in the next slide here, we have the body of that wait for nodes function. So we're going to do a while loop, a while true loop, and then we're just going to grab the lock, check the node availability. If there's enough nodes in the node pool, we'll go ahead and subtract those out and then unlock. Otherwise, we're just going to unlock and then wait until we check again. And then lastly, when we're done doing our work, we're going to lock and release the number of nodes. Okay. I wanted to mention that I/O is an important component of any workflow application. I didn't want to show a specific example here because there's a wide variety of mechanisms available for doing this. But I'll just move on from here. So to kind of summarize here, I want to talk about advantages and disadvantages of using Chapel for workflow, HPC workflow tools. So advantages: it's a modern programming language with modern features and productivity. It's got generics, type inference, native C, Python interop, and Fortran, which I haven't used much myself. But you name it, your favorite feature there. Parallel constructs built into the language make it really easy to write a lot of these patterns that I've shown. Performance is competitive, and performance doesn't always matter for these workflow programs, but sometimes if you're, in the case if you're doing like an optimization, like in a Bayesian optimization, the performance can become a bottleneck there. And then lastly, compiling and statically linking produces a dependency-free binary, which can be nice compared to, sometimes in Python, you have all these runtime dependencies, and it can be difficult to set up your environment depending on what those are. The major disadvantages are the compilation is time consuming. That's something that has been brought up earlier today, and we're working on. And the standard library and module ecosystem is not as mature as other languages, such as Python as an example. And I just wanted to acknowledge, there are lots of other alternatives for building workflows. I won't go through all these, but just wanted to acknowledge that there are other options. I think Python is probably the leading contender, and Python, I kind of called out the advantages of Chapel. Those are kind of in direct comparison to Python. In particular, doing things in parallel in Python can be challenging. Encourage you to go, look up how to do some of these tasks I talk about in Python and read the Stack Overflows, and you'll see there's about 10 different ways to do it. And the community doesn't necessarily agree on the way that one should approach it. But yeah, I didn't want to construct a straw man here and bash Python, so I'll leave that as is. So to summarize, developing HPC workflows is a challenge faced by many scientists and engineers, and Chapel has many appealing features, making it a competitive choice for developing workflows, as the features I mentioned earlier. So that's all I have for you today. Thanks for listening. Take any questions now.
So I have sort of a high-level question. So on your slide 3, you have this picture that I've seen before with the different parts of this whole workflow going on here. Maybe workflow is not the right word. I know that you have hyperparameters and feature selection currently. Are there immediate plans for the other portions? Have I missed that they're already in progress? That sort of thing?
Yeah, so those are still a long ways off, I think. I think so. Yeah, feature selection is kind of our next target beyond hyperparameter optimization in the data science pipeline. Yeah.
Okay. And then Akihiro asks, it looks like Forall plus process dot wait is more like an all-to-all sync. Would there be any way to do a P2P sync? Say, can one job wait on two specific parallel jobs?
Yeah, that's definitely possible, but yeah, that's not an example I prepared for this talk today. Obviously, I'm already running out of time with the examples I've shown. But yeah, that's that's not something we do in Cray HPO today, although we may need to for future genetic optimization implementations.
Yeah, definitely. And we've talked in the past about other models of like communication balance between like server client spawns and that sort of thing before, I know.
Mhm.
Well, that's all the questions that we have. Thanks again, Ben.
Yeah, thank you.